Magnets. Cool stuff. We saw with electricity that magnets and electricity are very closely related, right? We have the electric motors that convert electrical energy into mechanical energy. Then we have electric generators that convert electrical energy into electricity. All of that happens with the use of magnets in a generator. So you get a magnetic field spinning around, and that's going to generate a current. We're going to look at that and how all of that happens or plays out, and also what the deal is with compasses. How do they work? Moving electric charge is surrounded by a magnetic field. Remember, a magnetic field, just like any other field, is just this area surrounding the object, like we saw with the electric field. The area around a charge contained an electric field at various strengths. Same situation with magnets. Electricity and magnetism were regarded as unrelated phenomena until it was noticed that an electric current caused the deflection of the compass needle. Then, magnets were found to exert forces on current-carrying wires. Before we get into that, the guy who noticed the tilting of the compass needle whenever it was in the presence of a current-carrying wire, not educated, does not have higher than a high school diploma. Kind of an oddity that used to happen where you didn't have to go to a university to have your thoughts and ideas regarded. Then magnets were found to exert forces on current-carrying wires. The stage was set for a whole new technology which would eventually bring electric power, radio, and finally television. Starting off, 36.1 magnetic poles. Like poles repel, opposite poles attract. That's our objective. That's what we need to get down. Magnets exert a force on one another. They are similar to electric charges, for they can both attract and repel without touching. We felt this when we were playing with magnets. We know this. Like electric charges, the strength of their interaction depends on the distance of separation of the two magnets. Electric charges produce electrical forces, and regions called magnetic poles produce magnetic forces. The electric forces come from a monopole. There's only one pole. Meanwhile, a magnetic pole has to be a dipole, where there's two poles, a north pole and a south pole. We don't talk about a north pole or a south pole when we're talking about a charge, because that can be just one pole. Which interaction has a greater strength? Gravitational attraction between the scrap iron and earth, or the magnetic attraction between the magnet and the scrap iron? It has to be the magnetic attraction between the scrap and this big magnet. How do I know that? Because this stuff isn't falling down. If the earth was affecting this metal in a greater amount, then it would just have a greater pull than you could get the upward attraction. If you suspend a bar magnet from its center by a piece of string, it's going to act like a compass. The end that points northward is called the north-seeking pole. The end that points southward is called the south-seeking pole. More simply, these are called the north and south poles. All magnets have both a north and south pole. For a simple bar magnet, the poles are located at the two ends. In the North Pole, one magnet is brought near the North Pole of another magnet. They repel. The same is true of the South Pole near a South Pole. If the opposite poles are brought together, however, attraction occurs. So here we have this horseshoe magnet. I like to think of it like the cartoon magnet, the one we always saw in the cartoons growing up. We've got the North Pole and the South Pole. So the way the magnetic field works is you can think about it like the positive and negative. So the field lines will go out from the north and into the south. On this little disc magnet, the North Pole is on the bottom side, while the South Pole is on the top. Or the opposite if you flip it over. This is what I am talking about when I talk about a bar magnet. Little Bird says, beware of junk scientists who sell magnets to cure physical ailments. Claims for cures are bogus. We need a knowledge filter to tell the difference between what is true and what seems to be true. The best knowledge filter ever invented is science. Magnetic poles behave similarly to electric charges in some ways, but there is a very important difference. Electric charges can be isolated, as I talked about, the monopole, dipole situation, but magnetic poles cannot. A north magnetic pole will never exist without the presence of a south pole, and vice versa. The north and south poles of a magnet are like the head and tail of the same coin. You can't have both. If you break a bar magnet in half, each half is still going to be a complete magnet. So if we have a north pole and a south pole, and we snap it in half, now we have a north pole, a south pole, and a north pole and a south pole. So we just have two separate magnets. And a magnet always has to have a north pole and south pole. Break it in half again, and you'll have four magnets. Even when your piece is 1 atom thick, there are still going to be two poles. This means that atoms themselves are magnets. Here's what it looks like breaking the bar magnet. Every time you break it, north pole and south pole pop up. And it goes on and on and on and on and on. Think! Does every magnet necessarily have a north and a south pole? You know the answer to that. Let's get to it anyway. Yes, just like every coin has two sides, a head and a tail, some trick magnets have more than two poles. Time for the concept check. How do magnetic poles affect each other?